The question I want to ask to introduce the discussions over the next couple of days is how do we design AI, software, automata, automated agents to be collaborative players in a joint activity space when disruptions arise? And this question is important because right now and historically, agents, whether they're software, AI, or other forms of automata, misbehave and fail to coordinate. This creates a huge opportunity for us to architect new ways to carry out joint activity in networks of human and machine agents. Next. This is actually quite an old issue. And last month, by accident, notice this from the early 60s. And we found this in the Warhol Museum because he collected period pieces at ongoing basis and called them his time capsules. And this was the one on display. The machines are taking over. Computers outdo people at their work and soon will outthink them. This is an old story. Next. Right? And it illustrates that right now, this old story is operating at a new scale. And the forces have intensified to destabilize what's going on. And they're spawning crises that demand adaptation. And they are doing this at sector levels, at national levels, and at societal scales. Next. When this raises the classic question of when do people adapt? Next. When they have to. Next. So the question is not whether we have to adapt, but in which direction will we adapt? In these situations, what is common and comfortable is retrenchment. We retreat to cope locally. We go back into what we're comfortable and familiar with. But there's another way that history and research shows us, and that's a form of revitalization, where we reprioritize, reconfigure our activities, our relationships, and we move forward, creating the future. We find opportunities in the crisis. Next. Given these destabilizing forces at scale, which we'll talk about briefly, because I want to focus on the opportunity. We, all of us and our colleagues and those we work with and those we interact with are in a position where adaptation is necessary. And the reason is, right, the current trajectory from these destabilizing forces means that we are racing towards safety and systems engineering malpractice. Racing. Right? And malpractice, I'm referring here to a breakdown of the norms and processes by which we create safe and effective or effective and safe systems, thinking of engineering in the broadest possible terms. Now, the exemplar or benchmark failure to remind us about what's going on and exhibiting very vividly to us the effects is the AWS outage of last month, October 20. This is a wide swath outage in a layered and tangled set of infrastructures. These interdependencies led to a wide range of important disruptions to critical functions in a wide variety of sectors. This is an example we'll refer back to about how the destabilizing forces are producing challenges for us. Next. We've talked about this at the end of May in a piece that we published about contrasting the Silicon Valley way of move fast and break things relative to proactive safety. Next. Right. The mantra of move fast and break things was exemplified in a variety of contexts in that short piece. And the contrast is the mantra of proactive safety, or create foresight about the changing shape of risk before harm occurs. Harm can be a large-scale failure of a valued asset, resources, and capability that undermines many different goals and performance criteria, not just harm to people. And We see this in, for example, the AWS outage. So proactive safety looks like, oh, that's going to slow us down and be too thorough, when we need to move forward quickly in this aspiration that if we just push the technology and insert it and deploy it, we will find the value, we will get high value, and the things that break along the way are necessary sacrifices. The conflict between these two is stark, but it indicates to us that we can't simply sit back and say system safety, engineering for complexity, whatever it means. We just have to go slower because of the intensity of the pressures to just move forward that are operating at scale around us. Next. The second destabilizing force arises from a classic that little slide from the Andy Warhol Museum reminded us of, right? The pressure from our aspirations for large-scale benefits. If only we could deploy more autonomous systems. If only, right? This long-standing dream that somehow people are holding us back and the machines could take us forward, right? Now, what we have seen over and over again over my 40 plus years is, right, AI, software, automata, whatever the technology that creates the automation will misbehave. And that gets to be a bigger and bigger problem as the automation becomes more capable. Why? Because as it can do more by itself, people delegate more authority to it. As it can do more, it turns out that creates interdependencies. It creates other things that go on around it. As we'll see, and as some of our colleagues there at the meeting have said, no AI is an island. So as we have more capabilities and delegate more authority, larger consequences accrue. Now, this has been going on, and we have examples of this. You can look at the Strong and Wrong paper we put out. There are at least 5 different fatal aviation accidents from wrong and strong automation. Now, you can say, well, that was classic automation. But the death toll is between 500 and 600 people. These are serious failures, right, in the way that automata can misbehave. We've analyzed accidents and incidents in aviation. And again, right, the issue of how automation's behavior is fit or misfit to the situation, right, turns out to be critical. Why? Because automation is more capable and integrated more intimately into basic operations. The consequences of failure go up. Right? And again, this is illustrated with more modern critical digital infrastructures in the AWS case. The third destabilizing force, next. Oh, let me finish on this one. The second destabilizing force, right, is actually talked about quite a long time ago by Norbert Wiener. It's the risk of literal-minded automated agents, right? A system that can't tell if its model of the world is the world it's actually in. This means the system will do the right thing. Its actions are appropriate given its model of the world, its rules about handling that model of the world, but it's actually in a different world, so that its behavior is unexpected, surprising to those who are interacting with it, unintended relative to the design, the scope of the design and how it would handle things well, right? And it creates the potential or actuality of harmful effects. It is a set of mismatches between the automation's model of what model and activities relative to what's actually going on in the world. And it relates to creating demands for responsible people trying to supervise, manage, and redirect the automation activities relative to a changing world. In this situation, there's a huge premium on the cognitive ability to reframe, to recognize that things aren't working the way they normally do, the way they ought to, or even how even abnormal situations play out in an expected way. And by seeing these anomalies and unexpected, there is a drive and a need for reframing and revision of how we think about the situation. Right now, that is a uniquely human capability in the network of agents handling these situations. Next, please. The third destabilizing force is what we're all here for, right? It's the idea that all modern systems are distributed and layered. That's important too. Thus, all challenges are ones of coordination and synchronization. Right now, the emphasis has been and is ongoing again in AI Gold Rush #2, right? To think about things in the terms of a person interacting with a small set or a single kind of automated agent. And that continues to be the benchmark by which people characterize this. And it's important to recognize that everything is operating in a much larger network of an interaction where coordination, miscoordination, missynchronization are critical. So that has to be put first and foremost, right, in order to architect, design, and test for joint activity in a space of interdependent roles, multiple people and multiple machine and software actors, heterogeneous machine and software actors, right? Legacy machine actors as well as new ones, right? Multiple threads of activity are intertwined over different tempos of operation, right? Where there are multiple tangles across the layers of interdependencies operating. Again, all of these are illustrated at scale, right, in the AWS outage of October 20th. Next, please. The future is already here. These three destabilizing forces aren't brand new, right? And the effects and breakdowns in automation misbehavior and miscoordination have been seen before. It's really quite important that this is understood in critical digital services. That gives us a strong empirical base. And when we look there, which we did in an industry university consortium called Snafu Catchers, we found that breakdowns like the AWS outage are actually relatively rare. They occur regularly, but they should happen much more often. And the issue is, why don't they? And they don't because the incidents, the stream of incidents that are ongoing that threaten outages, threaten the viability of these critical valued services they deliver, are well handled. And they're handled, right, with a variety of tools and tooling, but by people. Some people with experience and expertise are able to catch the snafus that are regular. So our system isn't nearly perfect, isn't approaching effectiveness and reliability, but rather, right, the messiness, the difficulties, the snafus keep arising in a regular way. So that snafu catching, coping with that messiness, coping with complexity, what later turned out to be the positive capability of having graceful extensibility turns out to be essential in these systems. Next. So let's summarize this because we've talked about, studied, published papers, right, on the destabilizing forces, the effects, the consequences, the negative results that play out. The bottom line is, if we continue on the path we're going, and we already see strong evidence of this from Boeing, as well as SpaceX and others, the trajectory is racing towards safety and systems engineering malpractice. This is playing out in a context of growth, complexification, and adaptation, meaning that things are operating at new scales, which brings capabilities and performance potential, but also brings much larger consequences in a much more critical way when things break down. So this intensifies that question we started with and is the point of this meeting. How to design a network of AI and software agents. Let's borrow from Crow's, a murder of software agents, AI agents, to be collaborative, coordinative agents in a joint activity space when disruptions arise. That's the challenge that we face. Next slide. And we can adapt to pursue this opportunity by responding to the crises that are going on out there through revitalization. And the problem for us is not only do we have to do this the way these things have been developing, but now the powers of destabilization are creating these new sector, national, and societal scales. Next. So I want to talk about 4 positive developments so that we can architect these highly adaptive and layered networks. Right? First, derives from the theory of graceful extensibility and the empirical regularities and laws that underpin that, right, which is capacity for maneuver, how to adapt ahead in the approach to saturation as a way to cope with the inherent brittleness, the limits of any agent, any subsystem, any collection of agents, human, machine, machine only, whatever. It doesn't matter, given finite resources and continuing change. All systems can saturate. The second one we're going to talk about is looking ahead to track what agents in a suite of agents, a network of agents, will do next. What's next is the critical one. The third one is we have to manage a dynamic configuration of machine agents in pace with a changing world, given that you'll be facing risks and uncertainty. And that's a challenge for us. And the last one is how do we test and model this joint activity so we can assess whether we are making progress, whether we have sufficient capability to deploy in risky dynamic worlds. Next. Now, before I dig into those 4, I need to highlight some things that have come from some new scientific developments. These underpin the field of resilience engineering that I've been trying to develop with colleagues over the last 20 to 25 years. There are foundational theorems. In particular, we're drawing on my theory of graceful extensibility, though there's other related theoretical developments. All right, as processes of growth play out, as going on right now in AI Gold Rush 2, right? Complexification also goes on in parallel. New layers, new relationships, new interdependencies play out. And these create the conditions for adaptation, what we face, right? In responding to the growth of networks of software agents. Now, what turns out to be core and fundamental finding is that messiness is conserved. This is related to theorems called robust yet fragile, no free lunch, right, and others. So messiness is conserved over changes that aspire to improve systems. And we can use the heuristic of the messy 9, right, as a very simple way to map from the formal results and fundamental theorems to pragmatic action in a specific area, guiding how we might model and put together and architect networks that by which we would govern the interactions and coordination of software agents and human roles. And the messy 9 heuristic is very simple. There's 3 trios. Right? No matter how good how much you're improving a system, right, with your injection of new capabilities, the messy 9 will reappear. Congestion, cascade, and conflict will arise in new forms and in new ways and from new directions. Saturation, lag, and friction will apply, right? The risk of saturation, right, lag, delays, right, will lead to missynchronization, and friction, putting plan into action, will break coordinated activity, joint activity. All of this happens in the context of multiple tempos of activity that are going on interleaved, and surprise always occurs. And then ultimately, the real driver is the tangle of interdependencies across the different roles and layers. Next. So let's briefly hit things that we could do now in developing our new architecture of software and human agents. The first is how to adapt ahead of the approach to saturation. This turns out to be absolutely necessary, right? To mitigate the risk of brittleness for all agents at all scales. It's related to the concept of graceful extensibility as a fundamental property of all adaptive systems at all scales. Now we can show how this works as an actual control parameter, and we've done it at a couple different scales that are both realistic, right, and either mathematical or computational. Right? This happens not simply at a single agent level, but it happens in how to synchronize and coordinate across agents, because it turns out that while any single agent or role at any scale needs some form of extensibility as it approaches saturation, right, it turns out it can't have enough. Actually, for the same reasons it's required that you have some. Right? What ends up happening is it defines a new sense of reciprocity from Elinor Ostrom's work in social science and the Nobel Prize in 2009. So that reciprocity is other agents, other roles need to act to expand the capacity or offset the pressure on the unit that is at risk of approaching saturation. Now, we can see this quite clearly if you look at incidents that threaten outage in layered networks of critical digital services. And I walk through that in a couple of different examples in the YouTube link for the Adobe Research Summit 3 years ago. Next. Right. The second thing that absolutely needs to be in our network architecture and policies and protocols is the ability to see ahead, to see what's next. We have to see, given what has happened, what constraints are going on, how agents will act in the near future, right? It's necessary to keep pace with changing tempos of events, right? And it is actually one of the innovations that happened in AI Gold Rush 1. While everyone was pushing the AI as an island that would provide solutions on its own, what we quickly found in complex, dynamic, risky worlds, was that combining techniques for representation, seeing how systems really worked and how they malfunctioned, required visualization plus computation techniques. And you put those two together, you could see ahead. And we could do that with local out perspectives, right? And the ability to see what's happening nearby, near ahead. And also regional around perspectives, right? And perspective taking turns out to be critical and navigating over various perspectives. And we've actually designed that in a way, which we'll come to at the end, because it turned out while we designed it, it is insufficient relative to the scale of challenge we face today. In many ways, you can see this angle and direction on our architectures as that we need to build in a kind of dynamic field of interest that changes over time, that can be manipulated. How much am I looking ahead and looking around at what's nearby as these fields of intertwined activities play out? The constraint is that we don't have the tooling or tools, right, in the architectures or supporting the architectures to scale these techniques. We'll come back to that next. So this, in the next slide, give you a quick example of one way we've done a what next display for automation on the flight deck. We've demonstrated we use it as an analytic technique in doing assurance and evaluation studies, been developed by a set of colleagues, including Martijn Nisma, who's there with you, and Abby Post and Reneska, who's now at Boeing. And so we can start out with a projection of what will happen next by comparing a model of what we think is going to happen relative to what is actually happening ahead. If you go to the next one. And we have a new paper coming out. The link is in the summary, where you can look at an explanation of how this works in terms of when we recognize an automation surprise, how we reassess, how we project further ahead, how we redirect the automation, and managing the configuration of the suite of automated subsystems. In this process, we are able to quickly understand the kind of cognitive load that different kinds of disrupting events create, and the work that has to be done in order to redirect and keep things on track. We've been able to use this to evaluate proposals for new forms of automation in that context. This is an indication that this is in fact a feasible as well as necessary direction in order to see what's next, in order to reduce, right, automation misbehavior, automation surprise, and correct it within the time spans available given the tempos of operation. Next. The third and fourth ones I don't want to talk about much because you'll hear about that more from other speakers at the meetings today and tomorrow, right? It's how do you manage this dynamic configuration of machine agents and human activities to keep pace with a changing world, especially with the constraints of you're operating under uncertainty about what's ahead. Now, the current state from a study we recently did in one sector is that there's a very high demand on the human roles in the system to manage this dynamic configuration, right? And very minimal, if any, support at all for doing this task. It is an open question on how to do this and how to build in the principles and policies in our architecture that would make this go. It's a very challenging because in a distributed system, you can't solve it by having a single node, a single actor who acts as the command manager of the configuration. It will be overloaded and lag inevitably arises. Again, these are hard and fast constraints on how these distributed systems work. So we end up with this irony that managing the configuration of automata to match changing situations is in itself a joint and distributed activity. And it matters most when those messy 9 factors come back into play. And so that events that appeared to be easily handleable all of a sudden turn out to produce new forms of congestion, cascade, conflict, right? New forms of lag that threaten saturation, that create lags, right? That have to work effectively despite friction that delays things. It's particularly important when you look at this factor to recognize that most of the difficulties the messy 9 bring to bear as a testing heuristic, all right, come from the interaction across those messy 9. And we just did a podcast to introduce it that came out yesterday, where you can hear me talk about the messy 9 and how it plays out in the context of managing incidents in critical software services and how AI is affecting that process. Next. The fourth one is about assessing, right? How well can agents coordinate when disruptions do arise and how they can recreate and resume smooth, organized activities, joint activities following the disruption. That will be discussed by Martijn and Dane Murray and Mike Rayo, so I won't talk any more about that here. Next. What this brief tour of the requirements for revitalization of how we architect distributed systems of human and machine agents highlights a few things. One is that we have to understand the new science about growth, complexification, and adaptation in human and technological systems. We have to understand how stories of technology change, right? Need to see ahead to see the new forms of congestion, cascade, conflict, the messy 9 that will inevitably arise as apparent benefits get adapted to, hijacked, right, and utilized for advantage by human agents in ways that surprise the developers. The forces, the destabilizing forces I mentioned at the beginning, are producing instabilities across multiple scales. Instabilities means it's very hard for us to forecast and project and predict how things are going to develop. And we're seeing this all play out as intense struggles under pressure at wide scales, societal scales, and individual scales, as people adapt to workload overload and bottlenecks, crunching saturation risks at individual roles all the way up to societal roles, where we can talk about how the AI gold rush is saturating in terms of computation, data, energy, and money, and is trying to adapt locally in order to generate additional capabilities to offset the fact that they can't replenish or generate sufficient computation, energy, and money to meet the aspirations and growth that they want to, that they aspire to. Next. So where are we? I am really optimistic, and I'm optimistic because I know a fair number of the people gathered, and I know that they have the experience and capability to move forward and revitalize, building on the past successes in modeling distributed systems, right? To architect them in ways that can truly handle the challenges in front of us. Now, what does that mean for this meeting, right? Well, this meeting has to wrestle with some pretty interesting difficulties. First, we have to recognize that our distributed systems are inherently layered, and those layers are not pristine. They can't be mapped from the outside. They're not going to lay in neat rows for us or collections. They are intensely tangled, and our ability to take perspectives on these tangle of layered interdependencies puts perspective taking at the center. And navigating perspectives becomes a new kind of capability that's going beyond what I talked about with the seeing ahead and the what's next. And so building perspective taking and navigation in to handle the tangle of interdependencies and the cross-scale effects is going to be important. Two, it's a cross-scale problem. It's simultaneously about an individual role or a small collection of agents and human roles relative to things that are going on at societal scale, as in the AI gold rush. How do we coordinate over things going on simultaneously at these different scales? It's a challenge for how we understand, observe, and test our systems. And the next one is circular dependencies. You can see this, we highlighted if you go to stella.report, as we started our snafu catcher consortium and started looking at how all of these kinds of processes worked in critical digital services, and circular dependencies arose. They have arisen everywhere. They arose in the old nuclear power accidents I got started with. They arise in surgery in the operating room. Right. So a simple example of a circular dependency is the heart. And in the healthy heart, it's fine. Well, what does the heart do? It provides oxygen to vital organs. What is one of the vital organs? Oh, the heart. Right. Now that becomes critical when the heart is sick. And it creates a situation for sick hearts where you simultaneously want heart rate to be high and low. I want it high because I need to get more oxygen to the sick heart. But wait a minute, I want low blood pressure because the heart is sick, so I don't want it to work very hard. That cannot be solved in some absolute outside-in way. It can only be solved through expertise applied in the moment of balancing these conflicting goals, right, in order to escape the circular dependency. Now, these things go on regularly, and we can illustrate them at a broad scale, right? Where nuclear power, for example, is going to be a new source of energy generation to power AI server farms. However, the energy people say they can only build and operate in a cost-effective way the new energy production systems if they cut human personnel and replace them with AI. So now you have a circular dependency where, right, the energy system, right, depends on AI that supplies the energy that runs the AI algorithms on the server farms that support the system. Now you can say that's oversimplified for the circle of dependencies, a strange loop, but when you throw in the tangle of interdependencies, it becomes quite difficult. The next challenge for us is we understand and know how to deal with a lot of this stuff. We have to accelerate the scale at which we can do it. But what's held us back? We know a lot. The people in these rooms and these discussions know a lot about how to do the things I've talked about. Why can't we go further? It's because we don't really have the tools and tooling that can work at the scales in order to be effective on the broad and deep scales at which these systems need to operate. So we have new tools. We have new scientific theory. John Doyle from Caltech's Diversity-Enabled Sweet Spots gives us a formal nonlinear math kind of basis. My theory of graceful extensibility tells us a lot about how to set up and navigate different perspectives to look ahead, how to support adaptation in the face of these tangles of interdependencies, with a strong empirical base from studies of how people adapt to cope with complexity. All of these things are resources, along with much of the work that many of the people there have already done. We have a lot of resources on the table. And my appeal and optimism to everyone there is if we can look ahead in a spirit of, we know a lot, but it's not sufficient to handle the challenges in front of us, right? And that in order to seize opportunity out of crisis, if we can collaborate and coordinate together, innovate, and reframe how we approach these challenges, we can invent the future. Thank you, and I look forward to all the results and discussions and new ideas the meeting generates.